Okay, folks, the polls today will still be on Zoom because we just think it's more convenient. Don't worry about the attendance that we will get off the Zoom records. So if you're in the class, we know you're here, right? Let's wait. Let me wait for a minute or two. And in the meantime, if you have any questions from the last class, you can ask. Any questions? I guess not. Okay, let's start. So we're going to pick up where we left off 2 lectures ago. In between, we sort of took a brief detour to talk about modeling language, and that will become relevant next week. But for now, here's the story so far. We've seen that recurrent structures, recurrent neural networks, can be trained by minimizing the divergence between the sequence of outputs that the network produces and the sequence of desired outputs through gradient descent and backpropagation. The challenge is, how do you define this divergence between 2 sequences? Now, this is not always very clear. So, for example, if you were performing speech recognition, then the output is going to be a sequence of words, and the desired output is going to be a different sequence of words, and the 2 may not even be the same length. In this case, how do you define the divergence? So these are issues we have to worry about, and we will see how we can tackle problems of this kind in the next few lectures. So here are various variants of recurrent neural networks. This figure to the left is just a conventional MLP. The pink box represents the input. The green box represents the recurrent state, and the blue box represents the output layer. And in a conventional MLP, you just have the input going into the hidden states, which produce the output. So, and then this is a more regular recurrent network of the kind that we've seen so far, where you have a recurrent state which takes in a sequence of inputs, and at each time, the network produces an output. But then you can have other variants, like this many-to-one, where the network analyzes an entire sequence of inputs and then produces a single output. This you might use, for instance, if you were trying to recognize isolated words, where you listen to the entire audio and then say, yes, this is the word alpha. Or you could do this for sentiment classification. You analyze the entire input text and then say, yes, this has a positive sentiment. Then this second figure, this is more interesting, and this is particularly challenging. So here you have a sequence of inputs and you have a sequence of outputs, and there's an order correspondence between the inputs and the outputs. What I mean by order correspondence is that if the inputs occur, if you have inputs x1, x2, x3, x4, and then you have the outputs y1, y2, then you can sort of assign an order, meaning if you change the order of the inputs, this order would change. So there's an order correspondence. Instead of having x1, x2, x3, x4, if I had x3, x1, x2, x4, then the output may not be y1, y2 anymore. So the order of the input determines the order of the output, but then you don't have a one-to-one correspondence. So there's order correspondence, but there's no time synchrony. Is this making sense to you guys?
Not really. Like, isn't it always like, isn't the order of the input always going to affect the output? Like, if you have a time sequence, you just like randomly like shuffle the time sequence, the output is not going to be the same.
That's correct. So here, but then, so here, for example, there's something more to it. That's a good question. That here, x1, x2, x3 occurs before x4, and therefore y1 occurs before y2. So the order in which the outputs occur has a strict correspondence to the order in which the inputs occur. The portion of the input that corresponds to y1 precedes the portion of the input that corresponds to y2.
So do you mean like if x1, so like there's like two blocks basically, like this is like x1, x2, x3 is one block, x4 is one block, and if we shuffle x1, x2,
so let me give you
x3.
another example, right? Something that doesn't. So let me give you a counter example. A counter example is, for instance, if you're doing text machine translation, right? I ate something, right? I ate an apple. Now, if you translate this to German, it would say, ich habe einen Apfel gegessen. Okay. Now, look at what happens. Eat is the second word over here going in. Gegessen is the last word coming out. Apple is the last word going in, but the apple is the second to last word coming out. So there's no left to right correspondence between the input and the output in this particular example, right?
Yeah.
Whereas over here, there's a left to right correspondence between the input and the output.
I see.
That makes sense?
Yes.
Okay, so we're speaking of a strict order correspondence, but no time synchrony. That's the kind of problem we're going to be dealing with, okay? Now you can have other variants where you have a sequence of inputs and then a sequence of outputs comes out after the entire sequence of inputs has been analyzed. Or a single input can produce an entire sequence of outputs. So all of these are different variants. Now let's take a look at these one at a time. Let's first take a look at this guy over here, which is just a simple MLP. Here there's no longer any recurrence. If I have a sequence of inputs, I have a sequence of outputs. You have exactly as many outputs as inputs. But then there is no recurrence in that the processing at this time is not influenced in any manner by the process at this time. So the processing at the individual times is independent. Nonetheless, you can still use this to model sequences. So I could have a sequence of inputs, and the result, there would be a sequence of outputs. I could now define a desired sequence of outputs, and I could define a divergence between two sequences. And in this case, the fact that you're dealing with sequences gets captured entirely by the divergence, which is the divergence between two sequences. Now, you can sort of try to simplify this by saying that this divergence between two sequences is further simplified as the sum of the local divergences at each point, in which case the sequence dependence sort of breaks down. Nonetheless, the fact that you're considering the divergence between two sequences will influence how the model gets learned. So in this case, here's what would happen. You would have a divergence which is defined between the target sequence and the actual sequence. And of course, you're assuming a one-to-one correspondence between the target and the output, because that's how that's what this model really means. And so when you're doing back propagation, remember, to perform back propagation, you would need the derivative of the divergence with respect to each of these outputs. And that, in this case, is simply going to be the derivative of the local divergence at each time. So this just simplifies to a sequence of MLPs. And you can still use this in some manner of speaking to analyze sequences, although the model itself doesn't explicitly capture the sequentiality of the data in any manner. So here is a first poll to make sure that you actually understood what you're talking about over here. And let's release this poll. Yeah, the poll is on Zoom, and guys, you're going to have to bear with me. It's just some of you will not be able to see the poll. I don't know what the issue is with Zoom. It's unfortunate. Nonetheless, I'll show you the answers at the end of the poll. All right, so let me. Okay, guys, 5 seconds. All right. So here's what it is. The question was, conventional MLPs too can be used to model sequences. And of course, this is true. And when we use conventional MLPs to model sequences, the sequence nature of the problem is captured through the divergence, which is now computed between the output sequence and the desired output sequence. So most of you got this because almost everybody got this poll right. Now, let's consider this simple version of the problem, which is the many-to-many, where you have as many outputs as inputs. This is the kind of model that we've been talking about in previous classes. So this, for example, would be used in a problem like part-of-speech tagging of text. The network is going to produce one output for each input, but then the order in which the inputs occur is going to influence the classification of each input, the output for each input. So for example, whether some word over here is a noun or an adjective depends on what follows, and also on what comes before it. And so the recurrent nature of the model captures the sequential information, the dependence on the past and the future in making the predictions at each time. But then the key point is that for each input, there is an output. So here, for example, you would have a part of speech tag for every word in the input. Now, this kind of problem, it can be, the network could be unidirectional or it could be bidirectional. It doesn't really matter. The key point is that corresponding to each input, you have one output. Now, just for the purpose of explanation, I'm going to assume a unidirectional network, but clearly in a problem such as part of speech tagging, you really want the network to be bidirectional because words in the future affect the classification of the words at the current point, at the current time. Now, in this case, you're going to train using backpropagation through time. You would have, the network would produce a sequence of outputs. You're going to have a desired sequence of outputs. You would define a divergence between the two, and you'd use the derivatives of the divergence with respect to each of these outputs and backpropagate them through time to learn all the network parameters. So the first step over here, of course, is to compute the derivative of the divergence with respect to each of these outputs. And very often in this one-to-one correspondence situation, we're going to make an assumption that although in theory we are looking at the divergence between two sequences, we're going to assume that this divergence can be broken down into the sum of the local divergences at each time. And then when you do that, then the derivative of the overall divergence with respect to any output simply becomes the derivative of the local divergence with respect to that output, and that can be used for backpropagation. So
that would be then, oh yeah, I have a question about this. So yeah, that would be in essentially the same as for a normal MLP, except that it doesn't go through time.
Exactly.
Okay,
right? This simplifies matters a whole lot, right? And so here you have another pole. Chinmay, we'll get to that soon. Okay. 5 seconds, guys. All right, I'll end the poll. Yeah, some of you can't see the poll. It's unfortunate. I'm not sure why this is happening. Let me share the results. But let's look at what the actual question and the answers were. When you have this is what we call a time synchronous recurrent neural network, where you have one output for every input. Here you have one output corresponding to every input by definition. And the network itself can be either forward or unidirectional or bidirectional. So it doesn't really matter. Now, the divergence between the true and desired outputs can be defined as having additive contributions from the outputs at each time. We just saw this. So we've seen the first two kinds of models. Now let's look at this third kind of model, where you see an entire input and then produce an output. So this, for example, could be if you are performing speech recognition. A speech recording comes in, and at the end of the recording, you decide whether it has the word welcome or not. Or if you are performing question answering, you analyze the entire sequence of incoming words, and only at the end of it can you decide what the answer is. So, color of sky, you have to see the word sky before you come up with blue, because it could have as well been, color of milk, right? So you have to see the last word, you have to see the entire input before producing an output. Now, in this case, or speech recognition, right? So here, the inference is simple. You're going to get the sequence of inputs. It should be for speech, it would be the sequence of spectral vectors. For question answering, it would be the sequence of words. And then finally, at the very end, you're going to produce an output. But then here's the question. This network, as we know, is basically very symmetric, meaning every column is exactly the same as every other column. And yet, we are only getting the output at the final input. So what do you think happens at other times? Can anybody take a guess? That's correct, right? You actually produce outputs at those times, but you ignore it. You only read the output at the end of the sequence. Now, when you're training the model, you can define the divergence at this output. You have the actual output, you have the target output. You can define you compute the divergence between the two, and you can back propagate its derivatives all the way backwards through the network to update all the network parameters. But then this has a shortcoming. The shortcoming is that the network is actually producing outputs everywhere, as we saw. We just happen to be reading the output at the final instant. And this is basically pretending that there's no useful information coming from these two inputs, which is kind of wasting the information in those classification outputs. So here's a simple fix. I'm going to use these outputs too, and assume that these outputs are also going to give me an answer. Now, specifically, if I were performing speech recognition, for instance, I have a desired output R out here. I'm going to assume that every one of these guys should be classifying the input into the same class. So I'd be associating this class R with every one of these outputs. And now we have modified this model to your standard time synchronous model. You can define your divergence as the sum of the local divergence, a weighted sum of the local divergence. And then you can backpropagate this total divergence, the derivatives of this total divergence, to learn all the parameters of the network. Now, what is this weight? I'm looking at the weighted sum of these three divergences. That would depend on the problem. If you're performing speech recognition, if I'm saying, for instance, the sound R, then at each time, the output really is just R. So here, I can expect that each of these three must really have recognized the sound R. And so now all of these weights would be 1. Whereas if I had question answering, then I couldn't be answering blue when I see color or off. So in that case, you'd say that the weights for these two guys are 0 and the weights for the final output is 1. But this model over here sort of generalizes to both cases and has the added benefit of actually exploiting the classification outputs at the intermediate times also. So is that making sense? Questions?
Yes, Professor. One question. So
Yeah.
say we know that the third output is the one that we're really concerned with, but if we're producing all three outputs and when we're doing the inference, how would we decide that Y2 is the one that we need to keep and not any of the others?
Because this is the length. So you're producing the output at the final input.
Oh, okay. So sorry, what if you go back to our example which you started with, where we had an output after every 2, and then we had a block of 3 which produced an output, then a block of 2 which produced an output, and so we had this sort of a uneven distribution of inputs that gave one output each. In that case, how would
So we're going to get to that, right? But this is a simple problem, right? And so in this problem, it's very obvious what we must do, both for inference and for training, how we can use the excess information, right? For this problem, the question answering case should really make it clear. Color of sky. These things really don't make any sense. In speech recognition, you can assume that these outputs must also be the correct class. That's it.
I see.
Right?
Thank you.
Yeah. But then let's get to the problem that you discussed just now. What about this guy? How do you classify? How do you deal with this? And this becomes really problematic. This model, where you have order synchrony, but no time synchrony, where you have intermittent outputs. This is basically just a very simple concatenation of many copies of the simple model out here, right? As you can see, here I've got 3 different copies, but this simple extension by concatenation makes things extremely challenging. And where does the challenge come from? The challenge comes from the fact that you're going to be producing outputs at every time. You have no way of knowing which of these outputs to read, which of these are the real outputs. And therein lies a problem. So how do you deal with it? To deal with it, we first have to consider something. The point is, at each time, this network, the output of the network is really a probability distribution over all the classes. If you're performing speech recognition, it's going to be a probability distribution over all the phonemes in the language. And so at each time, the output is going to be, probability of R, probability of, B, and so on, right? Because this is a softmax and it produces an output distribution. And so now, when I have an input, sequence of inputs, at each time, the network is actually producing an entire probability distribution over all phonemes. The notation here is Y indicates an output probability. The subscript indicates the time at which the probability is being computed. And the superscript represents the symbol, the phoneme, for which the probability is computed. So YD4 is going to be the probability of the phoneme D at time 4. Is this notation clear to you guys? Okay, so now, once you realize that this is what the network is producing, then you can begin to make some progress. Any neural network with a softmax or logistic output is actually outputting this probability distribution, and a probability distribution of classes. When you perform classification, typically you pick the class that has the highest probability. So I can use the same principle over here as well. I can just go back here, and what I really, now remember, the real problem that we want to do is I have this sequence of inputs, x1, x2, x3, maybe going all the way to x100. And this is a sequence of phonemes, which could be, for example, bat, right? So the number of output symbols is lesser than the number of inputs. And we want to find, when you're using this classification paradigm, remember, your neural network is actually just producing a probability distribution over the classes, and you want to pick the most likely class. So we want to pick the symbol sequence. We don't know the length of the symbol sequence. When you see this, we don't know whether it's bat or, like donkey, right? With more fonts. And so we want to pick the symbol sequence S1, S2, Sk, which is most probable given the sequence of inputs. And so what the problem we really want to find is we want to find the symbol sequence whose probability is greatest given the sequence of inputs. Is this making sense? Questions? Everything builds off this. So if you have any doubts, all right, well, I'll just assume that you can.
I get this, but I have a small question about the question answering model. If you have many to one, and you have, for example, the question, the color of the sky, then like the information of the first outputs, like for the color and the color of, they don't really tell you anything about like the answer, which is blue, right? So how could you use that information if you don't have enough information yet to answer the question?
So at this point, I'm strictly speaking of speech recognition over here. But in fact, when you say color, then you're going to already be restricting your options to colors, right?
Okay, yeah, I see. Yeah.
So each of them is building up, right?
Yeah.
Okay. Anyway, so given that this is what I really want to be doing, then yeah, k is not equal to n. It's actually less than n. Or could be less than or equal to n, right? So k is not necessarily equal to n. Now, the simple solution for me is to just go ahead and pick the most likely symbol at each time. And when I pick the most likely symbol at each time, I'm going to get the sequence of symbols. And then I can begin merging them. So I find that these two are G. So I can assume that this entire sequence can be merged, and that at the final instant, I'm going to be outputting G. Then these are all F. So this is just one long instance of F. I'm going to be outputting an F over here. These are all E. So I output an E over here, and I output a D over here. So I just merge adjacent repeated symbols and place the actual emission on the final instant. Does anybody see a problem with this approach? Anyone?
Well, if it is noisy, then you're just going to have a bunch more of than expected.
Assume it's perfect. What is the problem?
Yeah, but if like let's say Y3F is misclassified, then you just increase the amount to 3 instead of just 1.
Okay, so even if everything is perfect, I'm not even thinking of misclassification. The key problem is that I cannot distinguish between two Fs and a single F, right? So you're losing the ability to distinguish, identify repetitions. And so, and also, you also have this other issue that the resulting sequence may be meaningless. What is the field? Who cares, right? So you need additional constraints. Now, one way to do this is to say, I'm only going to allow sequences corresponding to dictionary words. That's complex. It involves using a language model. We won't get into that. Or you can use a special separating symbol to separate repetitions. And we will see that in the next class. But for now, let's just assume that we have some way of obtaining an output from the network. I'm going to call this decoding. It is going to give me a sequence of it's going to give me an output sequence, right? So given an input, I can actually produce output, a symbol sequence, and say this is my best guess for the sequence of symbols that corresponds to this input. Now, the point is, this is actually a suboptimal decode in that even if the repetition didn't really happen, right? So if repetition, so somehow magically in your language, repetitions never happened. This, what you really want is the most likely small sequence. What you're really getting over here is, you know, B, 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 E, 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 F, 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 right? Or whatever, D, D, D. So this finding the most likely extended continuous sequence over here doesn't necessarily give you the most likely asynchronous sequence. So the most likely time synchronous output doesn't correspond to the most likely time order synchronous time asynchronous output. Can anybody tell me why that is the case? Anyone? If nobody can see why, so
Well, maybe let me just guess. So like maybe like from Y3 to Y8, if all of them like is if like the actual one is EH and like Y3 to Y8 EH like sum together is like larger, much larger than Y3 IY to Y6 IY, something like that.
yeah, well, you're right. So we'll get to that. Good answer, right? In any case, we've sort of partially addressed the issue of how to produce a sequence of symbols given an input. We'll have to go back and revisit this to see how we can do it right. Because as we just saw, what we are doing is that this problem is significant. And you'll see more of it in a few minutes, later in this lecture and the next lecture. But let's just assume that this problem is currently solved. The bigger issue is how do you train these models? Now, if you're trying to train the model, the training data ideally has two bits of information. It has the input, it has the output sequence, but it also tells you where in time the output symbols are produced. So for example, your ideal training data is going to say, here are my 10 input vectors. This is the sequence of outputs, and B occurs at 2, R occurs at 6, and T occurs at 9. If that happens, then things are easy. So this is what we will call an alignment of the symbols to the input. So here again, you have this 10 input of length 10. And when I tell you that B occurs at 3, R occurs at 7, and T occurs at 9, then I'm telling you that this portion, 0 through T, represents B, 4 through 7 represents R, 8 through 9 represents T. So this is an alignment of the symbol sequence, but to the input. Now, there can be many alignments for a given symbol sequence to an input. For example, the second one is a different alignment of but to the input. Here, the B is short, the R is long, and the T is long. Or here's a third one where all three are approximately the same length. So if all I gave you was that the output is B, T, that's not enough to know how the input aligns to the symbol sequence. And a single symbol sequence can align to the input in many different ways. So this information, so when you actually when you actually given training data, ideally, the training data must also have the alignment of the output symbol sequence to the input. So it must say, for example, that B occurs at 2, R occurs at 6, T occurs at 9. And when that is given, it's very easy to train your model. You can just compute, you just pass your input through the recurrent network. You compute the divergence for B at 2, for R at 6, for T at 9, or do the smart thing, you don't waste all of these extra outputs, and say, you can say that all 3 of these are B, all 4 of these are R, and all 3 of these are T. And now you have 10 different divergences that you can add. And so this total divergence is what you would minimize when you train the network. So is this making sense to everybody? What we've said so far? And okay. Any questions? No.
I had a question.
Yeah.
Can you please go over the order synchronous and the time synchronous part that you explained earlier? It's I'm not able to understand what exactly is order synchronous over here.
So the order synchronous is the portion. Time synchronous is there is one output for every input.
Okay.
Right?
Yeah.
Order synchronous is I have intermittent outputs. But the portion, the segment of the input that corresponds to any symbol that is that's in the output, these segments occur in the same order as the outputs themselves. So here, for example, x0, x1, x2 come before x3, x4, x5, x6, which comes before x7, x8, x9. And so y2 comes before y6, which comes before y9.
Right. But then what was the decoding aspect of it when we said that when we tried to solve the problem that we were facing while looking at the outputs?
So you don't know exactly if when you're just given the input, you don't know the times at which these outputs must be produced.
Right. Yeah, that was the case. That's why even when we combined the outputs, we could not see whether they were repeating or not.
That's correct.
So how are we? I mean, that part, like how we were solving the repeated. You said we'll go over this later, but
Yes.
okay. I mean, I guess I'll ask that again once we go over it later. Sorry.
No, if that's the question, hold your soul in peace for a bit, right? Because we are dealing with, yeah, we're dealing with a different problem here, which is when you're actually given training data, nobody ever tells you exactly at what instance each training symbol occurred, each output symbol occurred. So they're going to say, for example, here's a recording, and this is a recording of the sound of the word but. They won't tell you B ended at time 2, ended at time 6, and T ended at time 9. So in this case, how do I compute the divergence? Here, of course, computing the divergence was easy because I have the alignment. But now I no longer have the alignment. So how do I compute the divergence? Can anyone take a guess or any suggestions?
Small question.
Okay.
Is this model agnostic to the bigger chance of an A after the B, or is it or does it learn that as well?
No. So the order is given. It's the word but, right? And so Medhan and Madan, both of you have the correct answer, right? We're going to go through both of these. So first, we know how to train if the alignment is provided, but alignment is not provided. And the two solutions, as you guys just pointed out, is guess the alignment or consider all possible alignments, right? So let's consider the first solution. Let's start off by initially randomly guessing an alignment. I know it's the word, in this case, I'm using this horrible example, beefy, for some silly reason or the other. I keep planning to change it on my slides. I never managed to get it. So let's live with this example. So here, for example, I'm told that the word is beefy, right? So I'll start off by assuming quite randomly that the first B occurs at time 1, E occurs at 4, 4 occurs at 8, and the second E occurs at 9. This is an initial alignment. Now I'm going to train the model using this totally arbitrarily assigned initial alignment. And now that I've trained the alignment, I've trained the model, I will have a trained model. Then I can use the trained model to go back and re-estimate the alignment for each training instance using this trained model. And then I can use the re-estimated alignment to go back and train the model again. Now, what is this business of re-estimating the alignment? If I'm only given the output, the symbol sequence, then as we saw, there are many different ways of aligning the symbol sequence to the input. The alignment basically tells us which portion of the input aligns to what symbol in the output. Now, when I draw it this way, we can also see that this order synchronous output with an alignment actually corresponds to this time synchronous output. So do you guys see the relationship between these two, that these two are the same thing? Yes or no, right? I'd like to see some hands raised over here to see how many of you get this key piece, because this is key. I've got like 24 hands raised out of 200 students, which is kind of sad, right?
I have a
Okay.
quick question.
So,
Can
Madam,
you,
did you get this question?
No, my internet was off.
Okay, so here is given an order aligned symbol sequence. There are multiple ways of aligning it to the input, right? The alignment basically tells you which sequence of inputs corresponds to any particular symbol sequence. So here are different alignments of but to this input of length 10, but that basically means that this entire sequence of inputs corresponds, every one of these inputs corresponds to the sound b. Every one of these inputs corresponds to the sound a. Every one of these corresponds to the sound t. So these two are the same thing. That makes sense? Medan?
Yes, it makes sense. Yes, yes.
Okay, so now there's one difference. This guy here, if you don't see the alignment, this is just order synchronous, right? This one is time synchronous. And now I can think of this in terms of something called a compression or an expansion. So this, when I provide an alignment of an input of a order synchronous input, so order synchronous sequence to the input, I'm actually converting it to a time synchronous symbol sequence. So there are many ways of converting an order synchronous sequence to a time synchronous sequence. Similarly, if I give you a time synchronous sequence, then that time synchronous sequence can be collapsed by removing repetitions into an order synchronous sequence. So I will call this an expansion of an order synchronous sequence. And this I'm going to call a compression of a time synchronous sequence. Now, clearly, there are many ways of expanding an order synchronous sequence. And so also there are multiple ways of compressing a time synchronous sequence if you account for the fact that there may be repetitions. But if you ignore repetitions, then a time synchronous sequence can be compressed to an order synchronous sequence in only one way. This making sense to you guys? Okay. So our problem then is you're given an unaligned k length compressed symbol sequence S0 through Sk minus 1, and you're given some n length input where n is greater than or equal to k. when I'm trying to find, so remember what we were doing here was we guessed an initial alignment, we trained the model, and we're going to use that model to re-estimate the alignment. So the problem we have is, given a model, a current model, and this compressed symbol sequence and the input, we have to find the alignment, which means that given the compressed symbol sequence and the input, we have to find which of all of the various possible alignments is the one we must choose. And specifically, we want to choose the alignment that is most probable. So we want, in other words, we want to find the time synchronous symbol sequence, the most probable time synchronous symbol sequence that will collapse to this order synchronous symbol sequence. Is this making sense, guys? Okay, well, I have a few yeses. I'll go with that. And so you have a third poll. That's correct here.
Hello, Baba.
10 seconds, guys.
Yes.
Yes, I had a question in my time. So we
Wait,
have to
stop this
train
one.
and retrain.
There's a lot of noise. Somebody has to turn off their mic. But okay, let me show you the answer here. All but the last one were true. An order synchronous symbol sequence that is shorter than the input can be aligned to the input by repeating symbols until the expanded sequence is exactly as long as the input. We saw this, right? The alignment of an order synchronous symbol sequence is a time symbol synchronous sequence, because you're expanding the order synchronous sequence until it's exactly, by repeating symbols until it's exactly as long as the input. Now, a symbol sequence that is time synchronous can be compressed to a shorter order synchronous input by eliminating repetitions. We also saw that, right? So order synchronous symbol sequences that are shorter than the input are obviously compressed symbol sequence. Now, Rahul, that's what we're going to be talking about in the next few minutes, right? But this is clear. So now let's look at the problem of that UA mentioned. How do you find, given a model that has been currently trained and the compressed symbol sequence, how do you find the alignment, best alignment of the compressed symbol sequence to the input? Now remember that the actual output of the network is a complete probability distribution over all of the phonemes at each time. Again, I'm speaking in terms of phonemes, but this is a problem. This generalizes to any problem where you have order synchronous, time asynchronous outputs, right? So assuming we're performing speech recognition at each time, if these are your set of phonemes, you're going to be getting a probability distribution over all of the phonemes at each time. And so you could just pick the most likely phoneme at each time. If I pick the most likely phoneme at each time, will this give me an alignment of my desired target output? Anyone? Okay, Nikhil, why not?
I mean, the order of symbols might not be same as what we expect.
You may not even get, so here, for example, if my training symbol sequence is beefy, the most likely symbol sequence that you get from the model may not even have any of these symbols, right? If I'm just arbitrarily picking the most likely symbol at each time.
Maybe we need to account for like the chances of the transitions between the symbols, that there is like a bigger chance to get an A after a B or something like that.
Yeah, but the point is this. What is the first thing you would do? The first thing you would do is to ensure that you only consider these symbols, right? So you would knock off all the rows in this probability table that are not B, E, or F if your target symbol sequence is B, F, correct?
Yes.
You don't sound convinced.
Yes.
Thank you. Right. So now that means basically what I'm doing is I'm going to be pulling out the rows corresponding to my target symbols and then work only off of these. But if I just now, I can just decode on this reduced grid, and we are assured that only the appropriate symbols will be hypothesized. But if I now just go ahead and pick the most likely symbol at each time from this reduced grid, will this give me an alignment of my target output? Yes or no? Not necessarily, because they might occur in any order, right? Because here you're getting beef, beefy. I mean, this is not what you want. This is not going to, this over here, for instance, is B, E, F, B, F, E. Whereas what you want is beefy, right? It is sort of collapsed. All repetitions, and you find that this actually represents a sequence which is not what you want. So what can you do to make sure that the symbol sequence you get is exactly the symbol sequence that you want? Anyone want to take a guess?
Maybe we do something with transition probabilities.
So here's what I will do. I'm going to arrange the constructed table from top to bottom such that it has the exact sequence of symbols required. So for example, if my target symbol sequence, the training compressed symbol sequence for the training instance is beefy, then instead of just creating this compressed table by just throwing away everything that's not B, E, or F, I'm actually going to first pull out the B from this table and use it as my top row. Then I'm going to pull out the E and use it as my second row. Then I'm going to pull out the F, use it as my third row. And then I'm going to pull out E again and use it as my fourth row. So observe over here that if a symbol occurs multiple times, we repeat the row in the appropriate location. So here, for example, I've pulled out the B row, the E from this lower table, and I've copied the E row out here. Then I've copied the row for F, but then I've copied the row for E again. Okay. And so now, and then I am going to pull out the most likely symbol sequence from this, but now with a constraint. The constraint is that the first symbol has to be B. I know this because this is beefy, right? We're trying to get an alignment for beefy. So the first symbol has to be B. The last symbol has to be E. So I'm going to say that this final symbol over here is E. But then thereafter, I want whatever sequence I get to compress to exactly beefy, right? So which means that I can have things like sequences of B's, but then sequences of B's can be followed by must be followed by sequences of E's. They must be followed by sequences of F's, and they must be followed again by sequences of E's. So I'm going to say that the rest of the symbols must follow a path that goes monotonically from the top left corner of this table to the bottom right, where at each point, any symbol sequence can either be exactly the same as the symbol before it, or it can be the next symbol to the symbol before it. This sequence cannot skip a row. It has to go through every row and must be monotonic from top left to bottom right. Is this making sense, guys? This making sense? Right? And so how do you do this? Very easy. I'm going to compose a graph such that every path in the graph from source to sink represents a valid alignment of my compressed sequence to my input. Right? Remember, I actually have x0 through x, in this case, x8, right? Because I've got only 9 columns over here. And so this graph, basically it says that this symbol B over here can be followed either by B or by E. This B over here, so anytime you have a B, B can either be B followed by another B or by E. And E can be followed by either an E or an F. And F can be followed either by an F or by the final E. And so from each point, I have 2 arrows, one going directly right and one going to the bottom. And now any path through this graph is going to, such as this one over here, or if I just choose, say, a path over here, this path, let's say, just find a path through this graph. This path is going to obey the constraints that I mentioned earlier, which is that the path is going to be monotonic, and any symbol on the path is either going to be the same as the symbol before it or the symbol in the row above. So does everybody see how this graph is constructed? Because we have 2 rows for E, Madam. We have 4 rows, observe, right? That answer your question, Madam?
Yes, it makes sense now.
Okay, and we are going to, so Chinmay, because that is, you want the first symbol to be, remember, I'm trying to align B phi, right? So the first symbol must be B. And so this guy, the first symbol must be B, right? It cannot be one of the other 3. The last symbol must be E. It cannot be any of the others, right?
Right. So I was just considering the possibility of it ending somewhere in the middle. So would in
no,
that
but
case,
so this is the constraint. You really want a path which begins here and ends here. If it ends over here, for example, then that is not an alignment of B phi, right?
By middle, I meant like, let's say at time step 4.
So that's the
4.
part. If you stop at time step 4, it's not an alignment to the entire input, correct?
It could also end at E, right? At time step 4.
If it ends at E, what do you mean? So
I'm saying, let's say between time step 0, 1, 2, 3, it just goes diagonally from 0, like B, E, like this.
That's a valid path, right?
So okay, yeah. So we'll be saying that it's basically repeating at the end.
Basically
that's what we okay.
But that's a perfectly valid alignment, right? And we are going to be picking the most likely alignment. We're going to be picking the most probable path through this graph.
Right. Okay.
So in this case, like we have to change the model so that it can produce the softmax or the probability for repeated E's here, right?
No, the model is just producing this guy, right? The model is just producing this table.
Okay.
Right. Okay, and we just created this guy from it by copying the rows, right?
Okay, so like in the table above, the 2 E's will have the same probability.
Exactly.
Okay, I see. Thank you.
Okay, right. And so
quick question.
Yeah.
So here we're just predicting alignment. So would we have to have a different alignment matrix for every single sequence or input, basically? if we're removing the phonemes that don't belong to that specific
So each
output?
training instance is going to have a corresponding compressed symbol sequence, right? So, and so you're going to try to find the alignment of that compressed symbol sequence to that training input sequence.
Okay, perfect. That makes sense. Thank you.
Correct. So no, Rami, we are saying that you're going to be training. So you remember the first step when I said this over here, up here, we said we can start off by guessing an alignment and then training the model. You'd be guessing an alignment for every training instance in your training data, and then training a model over the entire training data. And then you'd be using the model to go back and guess the alignment for every instance in your training data. Did that answer you?
Oh, so did you iterate through this process and fine tune the training model and then figure out those like latent variables, which is the alignment, and then come back again and then iterate through this?
Exactly, right? So, and so how do we find the best path through this from the top left to the bottom right? That we want to find the most likely path, right? So now these are all probabilities. This table has actually got probabilities. YB0, for instance, is the probability assigned to the symbol B at time 0 by the network, by the recurrent network, right? So if I take any partial path through this graph, the probability of that path is simply going to be the product of all of the symbols on the path. So this partial path over here, the probability of this partial path is going to be YB0, which is the probability assigned to B at time 0, times YB1, times YE2, times YE3, times YF4. So this is the score for this path. This making sense to you guys? Okay. And now we want to find the path that is most likely. Now, one easy way of doing it is to, when we want to find the path whose total probability is the largest. Now, the easy way of doing this is to explicitly enumerate every possible path through the graph and then find its probability and pick the one that's largest. And that's going to be, depending on the nature of the graph here, it won't be exponential, but in the worst case, it can be really exponential and in the length of the input. So it can be really horrible. So clearly, you don't want to be, yes, Pranav, it's like a Markov chain. So you don't want to be doing something sort of exhaustive that is suboptimal. You want to use a dynamic programming algorithm. And so typically we're going to use a DP algorithm to find the most likely path from source to sink, like the Viterbi algorithm. Now, most of you are familiar with Viterbi, I assume. How many of you have heard of the Viterbi algorithm? First, lower your hands and then raise your hands if you've heard about the Viterbi algorithm. Some 49, 50 of you have heard about this. All right, so let's see how this goes. The Viterbi algorithm is 10-601 taught you well. It is like Dijkstra's, yes, right? It's breadth first though. Now Dijkstra's is not. So the basic idea for the Viterbi algorithm is very simple. If I want to find the most probable path from this node to this node, now observe that this node has only 2 parents, right? So the most probable path from here to here must either go through this parent or this parent. There's no other way of coming to this node. It has to be from one of these 2 guys, right? Number 1. Number 2, the most probable path to this node must be an extension of one of these 2 things, the most probable path here or the most probable path here. It cannot be an extension, for instance, of the second most probable path to this guy, because we know that the second most probable path to this guy already has a lower probability than the most probable path to this guy. So this means that the most probable path to this node over here is either an extension of the most probable path to this node or the most probable path to this node. That's it. Is that making sense to all of you? Right. That's a single yes. I'd like to see a few more yeses. I'll wait. Okay. If 20 of you get it, as far as I'm concerned, everybody got it. Now this logic is very simple, right? And so that is the logic we're going to use. I'm going to dynamically track the best path and the score of the best path from the source node to every node in this graph, okay? And at each node, I'm going to keep track of which was the best incoming node and the score of the best path, the probability of the best path to that node. And then eventually I'm going to compute the best path from source to sink. Now, here's what the algorithm looks like. I have some notation over here. The notation, observe that here I've got B phi, right? B, E, for E. So this is row 0, this is row 1, this is row 2, this is row 3. And the symbol at row 0 is B. So I'm going to say S of 0 equals B. The symbol at row 1 is E. So I'm going to say S of 1 is E, right? So the probability at any point is going to be Y subscript T. This is the time T. And the SR is the symbol, R is the row, and S is the symbol in that row. So S over here, this guy is row number 2, and SR is F. So is this notation making sense? Right. Each column is one sample from the training sequence, represents one sample from the training sequence. So is this notation making sense, guys? Again, each column over here, remember, no, okay, let me try that again. See this is YE phi, correct? So
Yes,
this 5 is the time T, E is the symbol in row number 1. Yeah?
Okay. Yeah.
Okay. So I'm going to use this notation and observe that, you know, S1 and S3 are both E in this case, right? So, all right, let's see how the Viterbi algorithm works. Now let's start at the leftmost column. The leftmost column corresponds to input X0, right? So X0 must be aligned to B. We know this. So which means that the probabilities of these 3 nodes, of the best path to these 3 nodes, is all 0, simply because none of these nodes correspond to an alignment of X0 to B. That making sense? So this is the only one that you retain. Now, the best parent to this guy, obviously it has no parent, so it's a -1. Okay. Then here's what we do. I'm going to go from left to right across time. At each time instant, I'm going to go from top to bottom. And for each node over here, I'm going to find the best parent. And then I'm going to compute the best path score to that node. So let's see, here's what it happens. So at each point, you're going to find the best parent. And what is the best parent? You're going to find the parent whose best score is the largest. So for example, if I were looking at this node has 2 parents. I will find which of these parents has the largest best path score, because the best path to this guy must go through the parent with the higher best path score, right? And so I'm going to first find out which of the parents has the larger best path score. And I'm going to keep a pointer to this guy. That's my BP. And then my best path score to the node itself is going to be the best path score to this best parent times the known score. So is this logic making sense to you guys? This logic? Right. Very simple. So that's it, because we know that the best path to each node must come from one of the parents. Specifically, the best path must come from the best scoring parent. That's a very trivial piece of logic. And so that's what we will do at the first time instant. This first guy has only one parent. So the best parent is going to be 0 itself. And the best path score is simply going to be YB0 times YB1. The second guy has two parents, right? And the best parent clearly is this guy, because this has a probability of 0. And so you're going to say the best parent is this one. And then the best path score is the probability of this times the probability of this node. And what are the remaining two? The remaining two, that doesn't really matter. Both their parents have score 0. So regardless of what you choose, the scores for these two nodes is going to be 0. Then you go to the next column. This one has only one parent, so I made a special case of it. So the best parent is this one over here. You're going to retain a pointer to this guy. Basically, the pointer is 0 over here. And the best path score is going to be the best path score to this node times the probability of this node. And then for the subsequent nodes, for each node, you're going to sort of find out which of these two parents, which of its parents has the higher score. It's either going to be the same row or the previous row. And if the node in the previous row has the higher best path score than the node in the same row, then the best parent is going to be L-1, where L is the row number. Whereas if the best path score to the node in the same row is higher, then the best parent is going to be L. So you're going to find out which of these two is higher, and you're going to retain a pointer to the parent with the higher best path score. And then the best path score to the node is going to be the best path score to the best parent times the node score as given over here. So if you go down using that logic, then you're going to find the best parent for every one of the nodes and also the best path score to the node. And you can keep doing this at each column, going left to right. First, find for you go down the column, and for each node, you find the best parent and maintain a pointer to the best parent. And then subsequently extend the best parent score by the node's own score to get the best path score to the node. So you do this for every node and keep going down the entire graph in this manner until you've computed the best path score and the best parent for every node in the graph. So is this logic making sense to you guys? Anyone with any doubts? No, right? Okay. This is easy, right? But then once you've done this, it's very easy. You know that at the final time, this is the only valid node, right? You know the best path score to this node. You know the best parent to that node. You know the best parent to that node. You know the best parent of 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 that node and that node. So you can actually trace the whole thing back. And by just tracing the sequence of best parents, you can find the best path through the entire graph. And this is going to be your guess, the most likely alignment of the compressed sequence to the input. And so you can, there's a poll. Yeah, the poll is active. Some of you are not seeing it. I didn't think of that. Thank you for giving me a quiz question. All right. I'm going to give you 5 more seconds, guys. All right, here you go. Okay, let's see. So this was easy enough. The Viterbi decoding finds the most probable alignment of a compressed order synchronous sequence to an input. And it's run on a table of probabilities constructed for the compressed sequence with 1 row for each symbol in the sequence, which is derived from the probability table generated by the network, by the recurrent network, right? Generated from the output of the recurrent network. It doesn't select the most probable symbol at in each column. It finds the most probable path through the entire graph, and there's no gap. And it's very likely that the symbol chosen at any specific time actually has lower probabilities than some of the other symbols in that column. But those guys just didn't happen to be in the most likely path. And so, Oscar, here you go. Here's what I have: the Viterbi algorithm pseudocode. I'd just take a look through that. But here's what we're going to do. We're going to start off by assigning, okay. So we're going to start off by assigning an arbitrary alignment of the compressed symbol sequence to the inputs for every training input. You train a model from those. Then from that model, you go back and align the symbol sequence for each input to the input, and that's going to give you a new alignment. And then you'd use the new alignment to go back and retrain the model. And here's something interesting. Once you have the new alignment, you're going to be computing the Kullback-Leibler divergence between this alignment and the actual output of the network, which is going to be the sum of the divergences at the individual times. And what do we know about the KL divergence between the target output and the actual output of the network? We know that when you use a one-hot representation of the target output, then the KL divergence between the target output and the actual output of the network is simply the, each individual KL divergence is simply going to be, anybody remember the formula for it? Anyone? What was it? Yes, but what was the formula? It just ended up being negative log of YB, right? At whatever time, correct? Remember this? Yeah. Don't forget anything. Everything pops up everywhere, right? So that means that this divergence is simply going to be the sum over all time of the negative of the log of the probability assigned to the aligned symbol at that time, right? So is this formula making sense? This one here. Is this making sense? I'm assuming it's making sense to everybody, okay? Basically, I'm summing over all time, and at each time, it is the negative of the log of the probability assigned to the aligned symbol at that time. And now when I take the divergence of this, the derivative of this divergence with respect to the output of the network at any time. Remember, the network itself produces a probability for all the symbols, all the phonemes, including phonemes that are not in the sequence, right? But at any given time, the divergence itself only considers the probability of the specific aligned symbol at that time. So as a result, if you look at the derivative of the divergence with respect to the output at any time t, it's going to have a bunch of zeros for all the phonemes except the specific phoneme that has been aligned to that time. And for that one phoneme, it's going to be the derivative of minus log of that probability, which just becomes -1 over the probability assigned to that symbol. So is this making sense, guys? Easy, right? And so now once you do that, it's very easy to train the model. Once you know this formula, it's very easy to train the model. To train the model, you're going to train all of your, you're going to initialize your alignments for all of the training instances. Then you're going to train the model with the initial alignments. Use those trained the trained model to go back and realign all of your training instances, and then use the new alignments to go back and train the model. And you can keep doing it till the probability, the best path probabilities converge or the alignments stop changing. Now this align and train steps can be combined into a single decode, find alignment, and compute derivative steps for SGD and mini batch updates. So instead of trying to align the entire training data, when you're doing SGD or mini batch, you're just going to be aligning the small subset of sequences in your mini batch and using those to update your model. And then you'd use the updated model on the next mini batch. So can I think of this as an expectation maximization algorithm where, like, it is kind of, it's like a hard version of expectation maximization, right? And so again, you could determine the alignments for every training instance and train the model, which is very kind of foolish, or better during SGD or mini batch descent. You basically align the instances in the mini batch and then use those alignments to update the model, and then use the updated model on the next mini batch. Now this has a problem, and this problem is, I'm going to take 30 more seconds, that this tends to be very heavily dependent on the initial alignment. If your initial alignment is really, really bad, then you're going to end up in poor local optima. If your initial guess is somewhat reasonable, then the model will keep improving things. But if your initial guess is so crappy that that training a model on that alignment gives you some junk, to recover from it in the training is going to take so much time that it's going to be inefficient. Also, you can just end up in poor local optima. So here's an alternate solution. In each pass of this training, instead of just picking the best alignment, don't commit to any specific alignment. Use all of them to train the model. So that's what we will have in the next class, how we can train the model. We will do this without explicit alignment. We're going to use what is called the connectionist temporal classification model. And we're also going to address the issue of, how do you deal with repetitions when you do the training, right? So Cedric and Medan, we will see how that is done in the next class. Any questions?
I have a question about the batch processing. So given a training sample, if none of the sequences are, let's say, similar, they would have a completely different alignment for the model, right? So
what do you mean? So the training is going to be a bunch of different training instances, right? And each one will have its own alignment.
Right. Yeah. So how is doing it in a batch helping us in training the model?
So that's So this is just the standard SGD, right? You're going to have some initial model trained to your random initialization, right?
Yeah.
Which could even be on just the initial mini batch, for instance, right? And then you're going to have some mini batch, and you know that every instance in that mini batch has to be aligned, right?
Right. Yeah.
So you could just align just that mini batch and update the model. Now the alternate is to align your entire training data and then go through this alignment in mini batches, correct? But the problem is when you do this, maybe you've improved the model over here, but when you've improved the model, by the time you get here, this model is already better than the alignment you had here.
I see. Okay.
Correct?
Yeah. Okay, got it. So it just gives us a little more steps for not messing up the alignment.
Yeah, exactly.
Okay.
The next 2 classes are also on Zoom, guys. I hope to be back next weekend. So let me stop the recording. Is the recording stopped?